You guys, welcome back. So we are to the last section in chapter 1.7, and this is all about word problems, or applications, as teachers like to call them. The first part, we're not going to do a whole lot with it. I just have a bunch of units of measurement for you, just to kind of see what that is, especially ones here in the US. So you'll notice these are all non-metric ones. They can get a little confusing. So we're going to jump right into the percent mixture problems. And what we're going to do is we're going to mix some different types of chemicals together, and hopefully we'll get a balancing thing going on. A chemist needs 100 gallons of a 40% solution, but has only 16% and 46% solutions available. How many gallons of each should be mixed to get the desired solution? So we're going to let X equal the amount of 16% solution. Now, what's left of the 100 is going to be 100 minus X. Now, that might seem a little weird, but let's say that X is 60. Well, how much is left over? Well, 100 minus 60, which is 40. But since we don't know what X is, we're just leaving it in terms of X. So this would be the amount of 46% solution. And I'm going to go ahead and draw 16%. So this is a beaker of 16% plus a beaker of 46%. And when I add those together, we should end up with a 40%. And here is the amount of 60, and we already know that the total should be 100. Notice when you add these two together, the X's cancel, and we end up with 100 gallons, like we should. So how much of this is actually the actual chemical that's in there? Well, that's 16% of that is. And how much of this is actually the chemical? Well, 46% of that is. And how much of the 40%, how much of the 100? Well, we know it's 40%, so 40% of the 100. There's our equation. So this is the amount of chemical in the 16% plus the amount of chemical from the 46% should give us our 100 gallons in 40%. 0.46 times 100 is just 46. Now, I do want to point out that you could multiply through by 100 to get rid of the decimals, but we really don't need to do that since we have a calculator. And let's combine up our like terms. So I'm going to go 0.16 minus 0.46, it's negative 0.3. Now, I'm going to go ahead and solve this by subtracting the 46. And divide both sides by negative 0.3. So I'm going to go 6 divided. It's a negative divided by a negative, so I don't need to bother with the negatives here. End up with 20. So 20. So X equals 20. So 20 gallons of 16%. And 100 minus 20 is going to be 80 gallons of 46%. So how much of each? There we are. To me, the tricky part is getting the setup there. All right, how many gallons of water? Now, water, we're assuming pure water, doesn't have any of the chemicals that are in this. So setting things up the same way, I'm going to let X be the amount of water. If you're having trouble knowing what to set X to be, for this first one, it could have been either, it didn't matter. The second one, how did I know it's going to be the amount of water? Well, the way I know that is because it asks how many gallons of water. So let X be what's missing. Make it nice and simple. So technically, if I want to do it this way, it's going to be 42% of the 10 gallons plus 0% of the water, right? There's 0% of the chemical in the water, should equal the 30%. Now, I want to point out the total amount of liquid that we're going to be getting is going to be the 10 plus the x. Once again, we're going to have water and 10 gallons of this solution. So what's the total? It's going to be 10 plus x. And they want to make that into a 30% solution. This goes away. And 0.42 times 10 is 4.2. 0.3x plus, and that just becomes 3. 0.3 times 10 is just 3, right? It moves the decimal one place. I'm going to subtract the 3, so I get 1.2 equals 0.3x, and divide, and I believe I'm going to get 4 from that. So 1.2 divided by 0.3. So x equals 4 gallons of water. This is called diluting it. All right. How many gallons of pure antifreeze? Now we're doing the opposite. It's just chemical. There's no water mixed with it. So instead of 0% like we did here, this is going to be 100% of it. So how many gallons of pure antifreeze must be mixed with 4 gallons of 50% solution to obtain an 80% solution? So now we're doing the opposite of diluting it. We're actually making it stronger. So I'm going to let x equal the amount of pure, or 100% antifreeze. And so this is going to be 100% times x plus 50%, 4 gallons there. Now I want to point out once again, kind of like up here, the total amount of liquid that we are going to have at the end is going to be x plus 4. And that needs to be an 80% solution. There's our equation. So this was bringing the percent down. This is what's bringing the percent up. So x plus, now 0.5 times 4, that's literally 1/2 of 4. It's 2. And 0.8 times 4, I believe, is 3.2. So 0.8 times 4, 3.2. So I'm going to move this. And I'm going to move the 2. 1 minus 0.08 is 0.2x equals 3.2 minus 2 is going to be 1.2. When I divide both sides by 0.2, I'm going to get 1.2 divided by 0.2 should be 6. It is. X equals 6 gallons of pure antifreeze. All right, moving on. This next one is going to be very similar. This is called a value mixture versus the percent mixture that we just did. And we are going to do this in terms of copy. Example 4. The manager of a coffee shop has one type of coffee that sells for $7 per pound and another type that sells for $15 per pound. The manager wishes to mix 60 pounds of the $15 coffee to get a mixture that will sell for $12 per pound. How many pounds of the $7 coffee should be used? So we're going to let x equal the amount of $7 coffee. And let's talk money now. 7 times x is going to be the amount of money it's going to cost for the $7 coffee, plus 15 per pound. And how many pounds of that? We have 60 pounds of the $15. So it's 60 equals, the price wants to be 12, and the total amount of coffee that we're going to have is going to be the X plus the 60. So you can see the setup is very similar to the previous ones that we just did. So 7X plus 15 times 60, that's 900, 15 times 60, 900. Let's leave 12 times 60 is 720. 60. Now I'm going to move my x's to the left. You can move to the right, doesn't matter. X's to the right. Seven x minus 12x is going to give me a negative 5x. And 720 minus 900 is a negative 180. When I divide both sides by 5, I get that x is 36 pounds of $7 coffee is needed. All right, we are now to a different type of problem. It's called uniform motion. And this is comparing distance, rate, and time. And here we define distance, rate, and time, what that means. You're welcome to read through that. I want to get to the formula, one that you probably know, distance equals rate times time. And the cool thing is we actually have two more ways, I should say, of writing the same formula. I could divide both sides by r and get that time is equal to the distance divided by the rate. Or I could divide both sides by the time and get that the rate is the distance over the time. The ones we're doing, I believe we're going to need this type here. Let's move on to our example. A twin engine plane can travel 200 miles per hour in calm air. Flying with the wind, the plane can fly 660 miles in the same amount of time it takes to fly 540 miles against the wind. Find the rate of the wind. So let's start there. Let x equal the rate of the wind. All right, so we need to be careful on this. It's always going to be the rate of the plane or the boat or whatever it is in calm air or calm water, plus or minus the rate of the wind or the current, depending on the type of problem that we're doing. So what I'd like to do is set up a table . Rate times time is distance. Rate times time equals distance. So I'm starting here, but I think we're going to be using this one here in just a moment. Let's change colors here. So with the wind, the plane is capable of going 200 miles an hour, plus the wind helps out. When it's going against the wind, the plane can go 200 miles an hour, but then the wind is slowing it down now. And how far can the plane go with the wind? Flying with the wind, plane goes 660. Against the wind, it can only go 540. And here is the key phrase that we want to point out. Same amount of time. That is the key with this one. Same for us means equals. Equals is an equation. We like that. So how can I relate distance and rate to give me a time? Again, I'm going to use this version of the formula. I'm going to take the distance, 660, and divide it by 200 plus x. 540, 200 minus x. And because it's the same amount of time, I'm going to set these two equal to one another. So 660 over 200 plus x equals 540, 200 minus x. Okay. So now I need to solve this equation. We're going to get some pretty hefty numbers here, but I'm going to do a process called cross multiply. So I'm going to remember something like this. And that's going to give me over here 660 times 200 minus x equals 540 times 200 plus x. And these are going to be some big numbers. Now you could divide both sides by 10 to drop those numbers down, but not a lot. Not going to save us too much. So 660 times 200, 132,000 minus 660 x equals 40 times 200, 108,000 plus 540x. Ooh. Now I'm going to subtract 540x to both sides. You could move the 660 to the right, it doesn't matter. And I'm also going to subtract minus 132,000. That's going to give me negative 1200x equals negative 24,000. I'm going to notice that when I'm going to divide here in just a second. When I do that, then negatives will go away. They'll reduce out. So let's do 24,000 divided by 1,200. That gives us a winner of 20 miles per hour is the rate of the wind. Cool stuff. So we could say that with the wind, the plane was going 220 miles an hour relative to the ground. And against the wind, it was going only 180 miles an hour. And now again, things are going to switch here, so I really want to emphasize this. This is the rate of the plane or boat that we'll have in just a minute. And when we're going with, we add the speed of the current or the wind. And when it's against, we subtract. So in this case, the numbers come first, the letters come second. This next example, that's going to change because we're going to have the rate of the wind or current. All right. So it took a motorboat 1 hour longer to travel 36 miles against the current than it took the boat to travel 36 miles with the current. The rate of the current, see, now we have the rate of the current. We want to know the rate of the boat. Before we knew the speed of the plane, didn't know the wind. This one, we know the wind, or in this case, the current, and we're to find the rate of the boat. So I'm going to start by let x equal rate of boat. I'm going to set up another table. So I'm going to say with again, against, rate, time, distance. All right, so let's start with the rate. With the current, that is going to be the rate of the boat, x, plus the current. Against the current, it's going to be x minus 3. Now, once again, this one, the letter is first because we don't know the rate of the boat. And it matters with the minus. It really matters with the minus, actually. Both are going 36 miles. Now, here's where it gets tricky. I'm going to use that same formula where I'm going to take the distance over the rate for the time. But to set them equal, we need to add 1 to this, because this is already an hour longer. So here we go. 36 over x plus 3 plus 1 to make them the same. And we get 36 over x minus 3. Oops, 3. Yeah, so we need to add 1 here to give it an extra. Yep. All right, my LCD x plus 3, x minus 3. And this is going to give us, when I multiply here, the x plus 3s are gone. I'm left with 36 times x minus 3. Plus 1 times all of that is going to be x plus 3, x minus 3. And here when I multiply, the x minus 3s reduce. There's our equation. Looks like we're going to end up with a quadratic, which is fine. And let's distribute. So 36x minus 3 times 36 is 108. This is a difference of squares, so x squared minus 9 equals 36x plus 108. And let's combine up our like terms. So we have x squared plus 36x minus, let's see what we get there. 108 plus 9, 117. And now that we have a quadratic, let's get everything over to one side. So let's subtract. So we get x squared, and it looks like 36x minus 36x, they're out. It's going to be minus 117 plus 108, 225 equals 0. So we got us a quadratic. We could factor it, but I'm going to go ahead and move that to the other side. X squared equals 225. The x equals plus or minus 15, but minus 15 doesn't make sense, right? When we're talking about a rate. So what's the overall rate of the boat? So the boat goes 15 miles per hour is the rate of the boat. All right. One more example. All right, so we have 2 cyclists start from the same point and ride in opposite directions. One cyclist rides twice as fast as the other. In 3 hours, they are 72 miles apart. Find the rate of each cyclist. Let's start here. Let x equal the rate of the slower. That means 2x, because it says one goes twice as fast as the other, is the rate of faster. All right, so let's set up our table. So faster, slower. Distance. All right, their rates faster is 2x. Rate of the slower is x. The time is three hours, which makes the distance rate times time is distance. This one was just straight up, no problem. So 2x times 3 is 6x. X times 3 is 3x. And I want to draw a picture so we get kind of an idea of what's going on here. So they start here. We'll call this one faster. This one slower. And in 3 hours, they are 72 miles apart. Which means when I take their two distances, 3x and 6x, if I add up 3x plus 6x, that should give me the 72. So this is the slower. Which means 2x is going to be 16 miles per hour. This is the faster. So make sure for every problem you have a let statement where you're explaining what your letters represent. You may have more than one that you need to set up, but yeah, just take your time with these. I know word problems can be a little scary.